contents of a location and storing the hash with the data. So it acts as a pointer as well as can check the integrity of the data.
Okay, good. Thank you, Shubham. So we have now started the recording, and so we have good understanding of what hash functions are and how they can be used. So now we will move on to the remaining slides of the same lecture. Just about 3 or so slides are left. So I'm turning off the camera and recording has started, and I will start sharing my screen. So we are here. So we are talking about basic crypto primitives and the hash functions. So these already we have covered, and we have also done a recap. So we remember what this is all about. Yeah. So we were on this slide last time. Just a quick glance through what this meant because we are in a bit of a hurry. So it shows that we have this hash pointer R1 pointing to hello world with that exclamation mark as we see. And if we change that data from exclamation to question mark, then this hash pointer will break. So we show it like this. So that means that we'll be able to detect that the content of that location that was pointed by R1 has changed. Now, in order to still bypass this, what one needs to do is that as the data is changed, okay, then because its hash will also change, if we update the hash pointer R1 to point to this location, and also now the value of that hash for hello world question mark, that is also something that we include in the pointer, then of course things will be in place. But that means that first of all, that it's not sufficient to simply change the data, but also we have to ensure that we have updated the hash pointer. So that is what we intend to explain in our last slide yesterday. And this is an example. Basically, this is something we have shown through the demo, and it's showing in a bit of more detail why it is a bit difficult to ensure that not only the data is changed, but the hash pointer is also updated when it is having certain properties to be satisfied, like number of leading zeros. And we have seen that if we talk about, say, 3 leading zeros, we have to try out 614 possible values of nonce if we sequentially keep searching for them. And if we see that just if we had the requirement of 1 leading zero, so at nonce value of 3, we would have achieved that. And as you can see, and as we have discussed, that it is not necessary that in between 0 and 614 we would have another possible hash value where 2 leading zeros were there. So maybe this 614 with 3 leading zeros itself also satisfies the case with 2 leading zeros. But maybe we saw that if we had say 11 as the value of nonce, we got some output possibly with 2 leading zeros. So this is how one can determine what would be the value of the nonce so that the required number of leading zeros can be obtained. Now, as we have seen through the this example, that if we have just one hash pointer pointing to one location, and where if the data is changed, we can easily detect that change. Okay. Now, we have, instead of just such one location, but now we have something like this this linked a number of such data values that are stored, okay, which we'll call later as actually blocks. Then if you see that there is this data di, and then di plus 1 is in the next block, and then di plus 2 in the next block, and so on. And it is, as you see, that as we mentioned, that this looks so much similar to linked list, except that these pointers are hash pointers. That's the difference. Okay, so there is some data in each such node or block, as we'll call it, and there is a pointer, and this is a hash pointer, so that if there is a change in di, then HDI will be able to detect that. And similarly, if there is change in TI plus 1, then HDI plus 1 will be able to detect it. Okay. Now you see that for the simple case where we had only one data and one hash pointer pointing to it, then if we had to change this data, like say if I wanted to change DI, then I would require to change HDI also, okay, because otherwise any change in DI will get detected by this hash pointer HDI. So we have to update HDI. Now you see that this HDI plus 1, that is a hash pointer for this entire data that includes DI plus 1 and HDI together. So HDI plus 1 would detect if HDI is changed. So that means that if DI is changed, it will be detected by HDI, and in order that that does not get detected, so this is what we are talking about, detecting tampering. So if somebody tampers DI, it would be detected by change in that HDI, this hash pointer will break, like we said that this hash pointer breaks. Okay, so HDI will break. Now, in order to fix that, someone who is trying to tamper with DI will also have to change HDI. But as soon as that is done, then this HDI plus 1, this hash pointer will break. Okay, so in order to fix that, then one has to also fix HDI plus 1, and so on. So there could be so many more after this third block that is on the rightmost block that we have here. So one will have to keep changing these hash pointers. But as we have seen that it's not a big deal, because as such generating the hashes is computationally very efficient. That we have already seen. Okay. So one can think, even if there are thousands of such blocks connected to each other, so if one wants to change DI, can keep on changing all of these downstream blocks, and one can ensure that the tampering that is done will go undetected. But there is the catch that all these, as we'll see, that these HDIs, these hash pointers, are generated in such a way that it is not simply based on the data DI, but it will also have to satisfy certain properties, like that number of leading zeros. So as we have seen that if the number of leading zeros is large, then generating the appropriate hashes will take time. Okay, so if one wants to change DI and then wants to update all these hash pointers down the line, which could be say 100 such hash pointers, now each of them will be taking a lot of time. So that's why it will become very difficult to tamper with the data once the data has been entered and added in one of these blocks, as we see here. Okay, so that is the crux of the thing, that this puzzle that one has to solve is computationally expensive, and as a result, updating a number of hash pointers is going to be computationally really expensive, and hence it becomes almost infeasible to do the tampering and then update all the downstream hash pointers. Now, that is something that we'll of course visit when we talk about how these blocks that we have in a blockchain, they get created and then they are connected with each other. Now, one other concept which makes use of these hash pointers in a tree, okay, and that is similar to that hierarchical hashing that we discussed earlier. Okay, so it is basically same concept. So let me just show it to you, that this hierarchical hashing that we had shown, it is basically this concept that is used, and this is what is called a Merkle tree. Now, what is done is that at the leaf level, we have what we call certain transactions. Now, these transactions are, for example, in Bitcoin type of blockchain, and again, we will discuss this in detail just to give you some idea at this stage, is that could be a payment that I make. So I pay, say, 5 Bitcoins to another person X. So that is what we treat as the transaction T1. Okay. Now, what goes in the leaf node, and similarly we have T2, T3, T4. So what we have is at the leaf nodes we have these hashes. So H00, H01, H10, H11. These are the 4 hashes corresponding to the 4 transactions T1 to T4. And then in one level above that, what we have is that H0, that would be the hash of H00 plus H01, and similarly H1, that would be the hash of H10 plus H11. So this is that hierarchical hashing that we talked about. And similarly, there could be more labels in between till we go to the root, and that root will have this hash of H0 plus H1. Now what it means is that these are again hash pointers, but organized in the form of a binary tree as is shown here. And if you see that now if somebody changes the value of that 5 bitcoins that I paid to X to 6, then what will happen, that hash value now will change. The hash of this T1 prime, that would be different, and as a result this H0, which is a hash pointer to pointing to this leftmost leaf node, that will break. Okay, so in order to fix that, one has to update that H0, and as we said that then one has to go and update. If that is changed, then the H root will break and so on. So one has to go and keep changing all the way up to the Merkle root. So the root is often called the Merkle root. Okay, so this is the way that we'll see later also, that the transactional information is stored as data in every block. So what we said here as di plus 1, so this is basically how the Merkle root is constructed, and as you'll see that the entire root need not be stored, but actually in the block header only the Merkle root is stored. The entire tree need not be stored here in the blocks as in the block header. So what we have is that every block, so this part that we showed, that you have the di and then we have some header component. So this header component is what is called the block header, and this block header, what it does is that and don't take it literally that this is exactly what is there in every block header for every type of blockchain, but this is just a representative figure which shows that in every block. So if you look at the block header in the middle, so you will see that it has got the Merkle root, or that is the Merkle root as shown here as part of the data that goes in this block in the middle. Okay, and then we have a block hash, and then the nonce, that is the nonce that was used to show that indeed some work was done to generate the block hash. Okay, and there are more stuff like difficulty level, etc., that we will cover later as we go into the details of these data structures. But just to see that this previous hash, that is the hash pointer pointing to the previous block. So it is the block hash that is there in the previous block header. So that will be the hash that is in the block in the middle. So if someone changes something in the block on the left, so the block hash will also change, and as a result this previous hash, this block this hash pointer, that will break. Okay, and this current hash, that is the block hash that is being shown in each of these headers, including the one in the middle. So that block hash will be computed, and based on the Merkle root and the difficulty level. The difficulty level is the number of leading zeros. So based on that only the block hash will be computed. So this block hash will have those properties that have been specified. Okay, and so on. So this is how the blocks would be chained together, and this is often called from a hash pointer. When we have these hash pointers connecting a number of blocks in a chain, then this is what we call as a hash chain that we get. Okay, so we'll see that blockchain can have this kind of representation in the form of a hash chain, but we'll see more details that what else goes in each of these headers. Okay, but overall we get an idea about what we mean by a blockchain, how the various different blocks that are stitched to each other by the hash pointers. Okay, but we have not yet discussed what is there in each block. That we'll discuss once we go to the appropriate lectures. So that brings us to the end of our first part of basic crypto primitives. Okay, so we'll move on to the next part, okay, where we will talk about digital signatures. Is there any quick question before we proceed?
Sir, can you just explain again why Merkle root is included in the block hash, a block header?
Right. So, very good question. Uh, what we want is that, see, this is the header. So there is some body of the block below it, which we are not showing. Okay. So now, if we change some values of the transactions, as I said, from that 5 bitcoins, it's changed to 6 or so. Okay. Then what will happen, as we have understood, that the this Merkle tree will get affected, and the Merkle root also will change. Like if we don't change, then that hash pointer will break. Okay. So in order to make things fix things here, okay, that change that somebody is trying to tamper and changing that 5 bitcoin to 6 bitcoin, that attacker will have to change all these hashes and all the way up to the Merkle root. Okay. Up to that, is it clear, Shubham?
Yes, sir.
Okay. Now you see that if we have the Merkle root here, now this block hash that we are showing here, this block hash is hash of what? This block hash, just at this level, again, I am saying that this is not the exact structure. We'll talk about it in detail later. But this block hash, if we consider that this block hash will be computed based on the rest of the components that you see here. Okay. So the block hash is a hash of this previous hash, Merkle root, and nonce. Okay. And it will generate a hash value which will satisfy, say, 5 number of leading zeros. Okay. As a result, and this block hash is now pointed by the previous hash in the rightmost block header. You can see that. Now, if we have the Merkle root here, then if somebody tampers with the data, changing that 5 bitcoins to 6 bitcoins, the Merkle root will change. And because the Merkle root will change, it will have a new block hash. Okay, because if this block hash itself is generated by taking into consideration the value of that Merkle root. Okay, if not, if somebody wants to check whether this block is correct, one can always check that the block hash that is being shown here is not the correct block hash for the new Merkle root. Okay, it was correct for the old Merkle root. Now, in order that an attacker also can go away undetected, the attacker will have to change this block hash as well. And while changing it, it will also have to ensure that the property remains satisfied. Are you with me up to this?
Yes, sir.
Okay. And now you see that if this block hash changed, then the next hash pointer will break. Okay. So then the attacker will have to also fix that that block header for the next block. Okay, and so on. So you see that for any change in the actual transactions, these are the transactional data we show that will be stored actually in the blocks, this T1, T2, etc. So anyone wants to change, that will cause a change in the Merkle root, and that Merkle root change will imply that the block hash will not match. So that block hash has to be changed, and then it will break and so on. So now downstream, as the previous hash in the next block is changed, then unless that block hash is recomputed, then again the next block point, the next hash pointer will break and so on. So that is the reason why we have the Merkle root as part of the block header.
Okay, sir.
Okay.
So like this recomputation will not be required if like a new block is added. Then
Of
won't the
course,
Merkle
yeah.
root change also?
Right, right. Sorry. So, no, you see that, say this is the rightmost block, suppose is the current block, right? So
Mhm.
what we'll see is that, so that will go into the, when you go into the details of how these blocks are generated, often we call as mining the blocks, we'll go into more details, okay, as
Okay.
to how the transactions are initially checked and then they are added in the blocks, and how it is ensured that it gets distributed to all the nodes in the blockchain. What these nodes mean, actually, these nodes are not nodes like these blocks here. These are our systems where we are getting the blocks generated. So we'll go into those details.
Okay, sir.
Okay, so now I will move on to the next set of slides that talk about uh, digital signature. Okay, So I hope now you can see my second set of slides. The entire screen is being shared. Okay, so now basic crypto primitives 2, and as we have already looked into these parts we have covered in the first set of slides. Okay, now we'll talk about digital signature. Okay. So we briefly mentioned yesterday about digital signatures and what regular signatures are all about in the context of, say, signing of checks and so on. Now, in digital signature, what we do is that we have a digital code that can be included with an electronically transmitted document. Okay. So there is a document, say there is a document which says hello world, okay, and then I am sending that document containing the text hello world to, say, someone, say X, okay, and then how would X know that the document that is being sent, okay, so that is authenticated, means that I indeed had sent hello world, and X also got hello world, okay. The identity of the sender, the fact that this was sent by me, how would X really know? And finally, that if X got that hello world message from me and he could verify all that, later on also, I cannot deny that I had indeed sent that hello world message. Okay, and that part is what is called, the third property is what is called non-repudiation. That means the sender cannot deny about the origin of the document. So these are the properties that we need a digital signature to satisfy. Okay, so we'll see how this is done. So what is the purpose of digital signature? The purpose is that only the signing authority can sign a document, okay, but everyone can verify it once it has been signed. That hello world message I sent to X, but if it is sent to X, Y, Z, anybody, so anybody would be able to verify that it was indeed sent by me. So it should not be dependent on X or Y or Z, but it should only be dependent on something that I can make use of, okay, which can be verified. And signature is associated with the particular document, and this signature that I put for this document hello world, that cannot be used for another one which says hi guys or something. Okay, so it is only for this document, and it cannot be transferred to a different document. So we'll see that. Now for this purpose, what is done is this public key cryptography, this technique is used. Just to give you a background, so these cryptographic techniques broadly fall under two types. One is what is called, usually it's called symmetric key cryptography, or often called private key cryptography, where the same key is used for encrypting a document and also for the decrypting a document. So if I use a key, say K, and encrypt a document D, then the ciphertext that we'll get out of encryption of D with K can be decrypted only with that same key K. In contrast, and we're not going into more details about symmetric key. Now for public key cryptography, which is also called asymmetric key cryptography or asymmetrical cryptography, so we'll call it as public key cryptography, or in general here we are all referring to only public key cryptography. So what we have is that there are a pair of keys. Okay, there is an encryption key and there is a decryption key. Now the encryption key is the key that is used to convert a plain text. Plain text is the one that one can actually read, and we denote usually that by M, to a ciphertext, though it is written here as M prime, so we could call that as maybe C for ciphertext. So M prime equal to encryption, so E stands for encryption of the plain text M using the key K, and decryption is the key that is used to convert the ciphertext to the plain text. That is, using the key K, one can decrypt this M prime to M. Now, let me clarify that this particular bullet, it does not specifically say about encryption and decryption using public key, or that is asymmetric key. So this is generally it is being shown. So this is, I would say that it refers more to symmetric key, where it is the same key that is used for both encryption and decryption. That is what we see here. Now, actually in public key what we'll have this K for encryption and another key say K prime for decryption, as we'll quickly see. Okay, so just do not get confused that we are using the same K here for encryption and decryption, but this is only the definition of what a key is all about. Okay? It is not specifically talking about public key. Now, properties of a cryptographic key. So that is for generally for cryptographic key is that the key is generated truly randomly, so the attacker cannot guess it. Okay. The key should be of sufficient length so that any brute force attempt to guess the key will be very difficult, and it should contain sufficient entropy. That means that all the bits in the key should be equally random, so that people cannot consider, oh, this particular combination of bits can occur more frequently, so let me first try out that. So it is similar to the notion of passwords. Okay, so it should be really generated randomly, and it is long, so it is not just two such character length or so. So we have this maybe 10 character password. Similarly, the cryptographic key also should be of sufficient length, and there should be sufficient entropy. So if all passwords start with S, so the attacker can always safely assume that the first character would be S. So that is what it means, that it does not have sufficient entropy. Okay. So similarly, in cryptographic key also, there should be sufficient entropy. And this again is general property of the cryptographic keys. The another important property is that, similar to what we discussed in the context of hash functions, is that so for the same key, even if the message varies a little, the ciphertext will vary a lot. Okay. Similarly, for the same message, if the cryptographic key varies a bit, then also the ciphertext will vary a lot. So this avalanche effect that we discussed yesterday, that also holds true for these cryptographic keys. Another important concept that we have to keep in mind, that the security, okay, of this we discussed here, the security of the whole system is dependent on the fact that the key is not known to anyone, specifically to the attacker. So the key is only known to the person who possesses that. Okay? And we'll see for public key cryptography who else can know which key. Okay? And the algorithm for actually encrypting a message with the key, that is well known, and it is everybody knows that, and that is the reason for doing that is that as we make these designs open, then what happens is that the entire community can actually check whether it has vulnerability. We do not want to go for what we call security through obscurity in terms of trying to hide the cryptographic algorithms. That is not what is done. The whole security is dependent on the fact that the key will be known only to the person concerned. Okay, so that is what we need to keep in mind. Now, in public key, what we have is that there are two keys. Okay, one is what is, as we said, the private key, and the other is what is called the public key. Okay. Now, let us take this particular example as is shown here in this figure. So it says that only Alice has our private key. So I would rather say that similarly, so on the right hand side it is Bob, and on the left hand side it is Alice. So Bob also has his private key, okay, which is known only to Bob, and Bob has a public key which is also known to everybody, including Alice. Okay, so just as Alice has a public key private key pair, Bob also has a public key private key pair, and this particular application that is shown, that actually makes use of Bob's keys and not Alice's keys. Okay, so what Alice wants to do is that Alice wants to send a message M, okay, to Bob, which only Bob will be able to decrypt and read. Nobody else in this world would be able to decrypt. Okay, so what Alice does, Alice encrypts this message M with the public key, that is kpub of Bob. So that is what we denote as kpub B. Okay. And what we get out of it is that M prime or C, that is the cipher text. Okay. Now this M prime is transmitted from Alice to Bob, and this transmission could be over any link where maybe there could be an attacker trying to snoop and will be able to get M prime, but from M prime one can get back to M only by using the private key of Bob, which is K prime Bob. Okay. Now what Bob can do is that when Bob gets the message, Bob will decrypt this, okay, using a function, so which again is shown here as E, and we'll have a little bit more clarity on these terms as we proceed, the notations. Now what Bob will do is that Bob will decrypt that M prime using his private key, and once he does it he will get back the message which will be same as that message M that was encrypted by Alice. Now any attacker who might have got access to M prime in between now will not be able to decrypt, because the only way to decrypt M prime is to know that K private of Bob. Okay, so only Bob can decrypt it. And also it needs to be understood that Bob's public key is known to everybody in this world, including Alice. So there is nothing that is hidden about the public. So there are various public key encryption algorithms, including RSA, named after Rivest, Shamik, and Edelman. And as we have already seen that the decryption key is the private key which is kept secret, and the encryption key is public, so anyone can encrypt the data. Like here Alice could encrypt, so I could have also encrypted the data with Bob's private key, I'm sorry, Bob's public key, and that also Bob would have been able to decrypt, and only the intended deceiver can decrypt that data. For RSA algorithm, we are not again going to go into all the mathematical details. We'll touch upon it, and we'll just take a look at one example for our basic understanding. Our goal is not to go into the details of understanding the complete algorithm and why it works and so on. So there are four broad phases. One is generating the key, distributing the key, then encryption and decryption. But we'll see that key distribution is fairly trivial. Now, this is the broad set of steps. So what it does is that it finds three very large positive integers, E, D, and N, and it is feasible to do that, and we'll see that it is fairly easy to do that, such that the modular exponentiation for integers M, they have this property. That means this E, D, and N, these satisfy a property that when we raise M to the power of E and then the whole to the power of D, that would be congruent to M modulus N. Okay, so we'll see how these E, D, N are related very soon, and we'll see some examples. But as we understand that this symbol, with these three bars, it depends that it is congruent. That means M raised to the power E whole raised to the power D mod N will be equal to M. That is the notation that is used. Now, even if you know, so these numbers are such that even if you know E, N, and M, so if you know this value M and N and also E, then it is even then it is extremely difficult to determine what is D. Okay. Now you can note that M raised to the power E whole raised to the power D congruent to M mod N, that we can also see that M, it could write M raised to the power D raised to the power E. So that means this E and D, these can be interchangeably used. That means if I encrypt the message, this M is, we'll see that it is like that value that we are raising to the power of E to the power of D. And if we consider E to be the encryption key, that is the public key as is written, so E in conjunction with N and D in conjunction with N is the private key, then if we encrypt a message with the encryption key, that is the public key, then it can be decrypted with the private key which is dn. In contrast, if we encrypt the message with the private key, that is this d and n, then it can be encrypted with it can be decrypted with the public key en. Okay? So any message encrypted with the public key can be decrypted with the private key. Any message encrypted with the private key can be decrypted with the public key. That is the crux of it. That is what we need to understand. So m is the message that needs to be encrypted. How is it generated? So this is the overall idea, and we'll quickly go through how these are generated. So what is done is that two distinct prime integers, very large prime integers, p and q, are initially chosen and at random. Then we compute n equal to pq. So n is the one that will be used as the modulus. That is what we are talking about here. The length of n is called the key length. We compute what is called this phi n, which is called the Euler-Taussian function, as p minus 1 into q minus 1. And then we choose now an integer e. So this e will act actually as the encryption key. E is between 1 and phi n, and it is relatively prime to phi n. Okay. So that is GCD of e phi n is 1. That is really simple to understand. So that is how we first choose the encryption key. So choose an integer. So there could be multiple such integers that satisfy it. And then once we have chosen e, then we determine e as e inverse mod phi n. So that is how d is chosen. So this d again is equal congruent to e inverse, okay, modulus phi n. So that is d is the modular multiplicative inverse of e mod phi n. So note d into e equal to e mod phi n. So that means that d, it is very simple to understand that e is first chosen, okay, and then we determine d such that d into e is congruent to 1 modular phi n. So let me take an example so that it will be very easy. So right after this slide, we'll go to the example. Okay. Now, once we have got this encryption key e and the decryption key d, okay, then let us see how we encrypt any message. So let m be the integer representation of a message m. So we have a message m, we have an integer representation of the same, and then encryption is done with the key, that is en, as we talked about here, that en is the public key. So e, we can easily remember, is for encryption. Okay. So what we get is that the ciphertext that we'll have is c will be m raised to the power e mod n, and then when the c is transmitted to the receiver, in the previous example that c was transmitted to Bob, and this en is the public key of Bob. So Alice used this en to encrypt the message m to generate the ciphertext c, and then once Bob gets that ciphertext C that is transmitted from Alice, then what Bob does is that Bob uses his private key for decryption. So Bob will be doing what? Bob will be using that C, and basically the symmetric process is done. C is now raised to the power D. There M was raised to the power of E. Here C is raised to the power of D, and D is known only to Bob, and then C raised to the power D mod N. That is computed, and if that is computed, we can see that c raised to the power d is this is simple modular arithmetic, and we can have this easily derived that c raised to the power d mod n. Now c, if we replace with m raised to the power d mod n, and then we can do some simplification, we get m raised to the power d raised to the d mod n, and that will get back to m. Okay. So we take an example here which will clarify the whole thing. It's actually fairly easy to do, and in our whole this course, we are not going to actually try to run these algorithms ourselves or try to implement these algorithms. We'll see how to do that. So let us see the one particular example. Okay. So as we first said that we have this key generation, key distribution, encryption, and decryption. So we have studied all these, how the keys are generated, and then distribution is basically that I am generating the keys. So like in this example, suppose I want to generate my public key, private key pair. So what I will do is that I will go step by step. So as we see here that we select two prime numbers as was discussed here. So we are running through the same set of steps with examples. So we choose two prime numbers, 17 and 11. We calculate n equal to p into q, which is 17 into 11 equal to 187. And then we compute phi n, the Euler-Tochian function, which is p minus 1 into q minus 1. Of course, for relatively these prime numbers, that is how it is defined, and we get it as 160. Now we have to select E such that E is relatively prime to phi n, that is 160, and less than phi n. So this is the step that we talked about. Choose and in the fourth step, choose an integer E, and it should satisfy these properties. Is that we choose E, and let us choose E equal to 7. Okay. As we said that there could be multiple such E's which would satisfy, and we choose E equal to 7. Now what we have to do is that we have to said here that we have to determine D such that D into E is equal to 1 mod phi n. So determine D such that D equal to 1 mod 160, phi n equal to 160, and D is less than 160. Now so we can how it is computed, we are not going to that details. Okay, certain theorems can be used to actually determine it. Now we can see that D equal to 23, that satisfies, because 23 into 7 as we see equal to 160, sorry 161, which is 1 mod 160, right? So 23 does satisfy the requirement for D. So now what we have is that we have this E equal to 7 and D equal to 23. So suppose I have denoting this, okay, and then if I want to encrypt a plain text, say M, and that is say this integer 88 itself, then how do we create the ciphertext? So ciphertext will be, as we have seen previously, that ciphertext will be m raised to the power e mod n. So it is 88 raised to the power 7. Okay, as we see, e is 7 mod n, and n we have seen is 187. And now this modular operation that can be actually broken up like this. So we have, instead of raising 88 all the way to the power of 7 and trying to do it, and of course as you see that he could have been much larger and raising would have been difficult. So one can actually break it up like this to make the arithmetic simple, and one can follow this simple arithmetic and see that we'll end up getting the value of ciphertext C is equal to 11, as is noted there. So if for example I generated these keys, then and I am Bob, then Alice would be knowing this 80 this sorry this 7 and this 187, and then based on that what Alice would be doing is that Alice wants to send that message M to Bob. So Alice is doing all this, generating the ciphertext and getting the ciphertext value of 11. So that is what we had seen here, that Alice got that 11, that is the C or M prime as is shown here, and then Alice is sending this over some channel, and what Bob gets is this ciphertext 11. Now what Bob does, that Bob knows that the decryption key 23 and nobody else knows it. So what Bob would do is that Bob would raise 11 to the power of 23 and then mod 187, and then with this simple arithmetic, etc. And you can see that finally what we get is that the last line, that it is whatever 797202245 mod 187, and that comes out to be 88, which is same as the original plain text, that was M. Okay. So that is the whole set of steps with this example as to how things work. Okay. For sending a message from Alice to Bob using Bob's public. Okay. So that is what is done. Now remember that we started in the first slide, we said we will talk about digital signatures, okay, but we have not yet talked anything about digital signatures. Okay, we have only said that if anyone wants to send a secure message to me, they will have to encrypt the message with my public key, and I'll be able to decrypt with my private key. So it has nothing to do with digital signature here. And this particular example was taken from this book by William Stallings, as is mentioned here. What we'll do is that in the next step, let me again take you through a demo, okay, which you will see that it's so easy to actually work with this type of encryption and decryption. So, so this is a freely available tool online, uh, and you see that it is talking about generating RSA key, and it is talking about key size is 1024 bits. Now you see what I do is that I click on generate RSA key pair and see that immediately it gets generated. So of course, although we said so many steps and all that, but actually you can see that generating these key pairs, it is pretty efficient. Okay. So we have got this public key and private key. If anyone, if you have public key, your own public key, private key pair, you could now do the next steps. But here I could use generate this public key, private key. Okay. Now what we do is that we have to enter a plain text and say I write hello world. Okay. And then what I want, suppose I am now, let us consider that I am or say I am sending it to Mr. X. Okay, so this public key private key pair is of whom? Is it mine or is it of Mr. X? Anyone can suggest? Any idea? What I'm saying
If
is,
you're
sorry?
sending to Mr. X, then the public key you will be using is of Mr. X.
Right. Good. So that means what? That means that what I generated here, these are not mine. That is as if Mr. X has generated this, and Mr. X has made this public key available to the entire world. So I also know that the public key of Mr. X is this one. Okay. So now I want to send the message hello world to Mr. X. So what I do is that I write hello world, and then I enter Mr. X's public key. Okay. And then what we do is that we select here that this is the public key, and then I say encrypt. Okay. And as it is done, so I get this as the output. Okay. This is the encrypted output, that is the ciphertext, and it is written in base 64 and all, don't bother about it. So what I do is that I send this encrypted output, okay, to Mr. X using some channel, and Mr. X has now got this as the input from me. Okay. Now Mr. X gets some such base 64 encoded something something, and then Mr. X will now need to decrypt it, right? So what Mr. X will do? Mr. X will use his private key so that he still does not know what I have sent. So he has this private key, and we say, oh, this is the private key, and we say, so Mr. X has decrypt, and see what Mr. X has got. He has got hello world, right? So that is a simple flow of how this public key can be used for sending secure messages. Okay, so that is use of the basic use of these cryptographic techniques, but we are not up after that at this stage, right? We have been talking about something else called digital signature. So let us see what digital signature is all about. Now, digital signature is that now suppose Alice wants to send the message hello world to Bob, but Bob will have to understand that the message has indeed been sent by Alice, and the message has not been changed on the way. Okay. In the previous example, there is no way the message could have been changed on the way because the attacker would not know the private key of Bob. But here what we want is that we want Alice to send a message. Okay. So Alice will sign the message in such a way that anybody else can check that the message has, first of all, not been tampered, and the message was indeed sent by Alice. And also the third property, if you remember, we had discussed at the beginning of this set of slides that Alice cannot later deny that she had indeed sent the message. Okay. So what Alice would do is that now Alice would sign the message with her private key. Okay. So if this is the message M, now you see that it will be this signing the message is simply encrypting the message with now K private of Alice. Okay. And we get M prime. And then now this both M and M prime are transferred. Okay. So the message in plain text is transferred. So M is message in plain text. Okay. So hello world is transferred, and that M prime, which is that message encrypted with the private key of Alice, that is also transferred. Now once Bob gets it, so Bob sees that, oh, there is a message called hello world and Alice has sent, but is it indeed what Alice had sent, or some attacker in between from hello world changed to hi guys, or it was Alice had sent hi guys and some attacker changed it to hello world. Bob does not know. Okay. Also, how would Bob know that indeed it was sent by Alice and not by somebody else? Okay. So what Bob would do is that now Bob would apply Alice's public key, which is known to everybody, including Bob, and then once Bob applies that public key of Alice, then what Bob would get is that Bob would get back something, say M, and that M would match with the M that was sent by Alice. If you remember, we said this, that any message, if it is encrypted with the public key, it can be decrypted with the private key. If it is encrypted with the private key, it can be decrypted with the public key. So in this case, we are doing the reverse of what we discussed in up to the last slide, that the encryption is being done by the private key and it is decrypted by the public. Now you see that it guarantees all the three requirements. That first of all, that Bob indeed knows that because the message could be decrypted by the public key of Alice, okay, then it must have been encrypted by the private key of Alice. Otherwise, it could not have been decrypted. Okay, so Bob knows that the message was indeed sent by Alice. Second thing is that because the decrypted value matches with what was also sent in plain text, that is that M that we see here just below the arrow. So Bob also knows that, oh, this was actually the message that was sent by Alice and it has not been tampered with in between. So Bob knows that it is indeed the same message that was sent. If only the M was sent, any attacker could have changed it, right? So that's why we are also encrypting the same with the private key of Alice. Also, finally, that if later on Alice says, "Oh, I never sent you that message, hello world," then Bob can say, "How is it possible? Because this message that I got, that I could decrypt with your public key, so that must have been encrypted with your private key, and that private key is only supposed to be known by you. So you must have sent it." So Alice can later on see that if it was somehow stolen or something, and that's a different issue altogether. Okay, so that is what will be done when we talk about this digital signature. So
Sir,
let me, yeah, go ahead.
sir, if M is tempered, then we can't know, like Bob can't know that who sent the message, right? Because
No,
the
no. If M is tempered, if M is tempered, so Bob would know that whatever was sent in plain text M, that is not matching with what he got by decrypting that M prime, right? That will not match. Okay, so Bob will immediately know that what was sent as M is not matching with what was encrypted by Alice. Okay, so Bob would immediately come to know that the M that was sent, that was indeed tampered.
okay, so in this case we know that Alice sent the message, right? But if we
Yeah,
don't
yeah.
know who sent the message, then we
Yeah.
can't know.
Oh, of course, of course. You know that that is why. See, that is why this M and M prime. So Alice is sending this thing to Bob. So Bob knows that the originator is Alice. Of course, you are very right that you have to know that I have to apply the public key of Alice. So I know that the message was uh, sent by Alice. But because that was sent by the attacker, and it was encrypted by the private key of the attacker. Did you follow?
Yes, sir.
So, sir, Alice has to send the public key every time she's sending the
Oh,
message.
very good point. Now, so let me clarify that point. As I said, that the public key is known to everybody. Okay, so if we see these steps here, okay, yeah, sorry, key distribution. Okay, so now what happens is that, of course, that first of all, uh, Bob has to know the public key of Alice. So you can assume that Alice has made it public, like Alice has posted it on her website, and everybody in this world knows about the public. So you can consider that that has been made known to everybody in this world. So that means that Bob also knows it. Okay, so it is not that Alice has to send the public key every time. Now in this one we are not seeing public key being sent. Okay, it is assumed that Bob knows the public. So, but of course, all of us really do not try to know everybody in this world's publicly, right? So it is basically done like this, that, and it is not that Bob is having the key somewhere, right, or keying it in and things like that. So usually what happens with the people that we interact with for keeping their public keys, we maintain what is called a public key ring. Okay, so it is basically I interact with maybe 20 different people, so I have a public key ring which will have the public keys of all those 20 people. Okay, and based on whoever is sending the appropriate public key will be applied. Okay, so it's like that. So it is not that and I might be actually interacting with Alice again and again. So it is not that Alice is sending me the public key again and again. Okay, so that is not required. So basically one can maintain the set of public keys and automate and have a script, and which will know that, oh, if it is being sent by Alice, you apply this public key and so on. So that is how it is handled. There is one other important concept that I am just making a mention of. I am not going to discuss this at all. Is that how indeed you know that if Alice says that, oh, I am Alice and this is my public key, how would I really know that this is Alice who is saying and not an attacker who is claiming to be Alice and saying that, oh, this is my public key? Because if that is done, so if the attacker does it, okay, then what would happen is that I might think that I am sending a message to Alice by encrypting it with her public key, but actually it is the attacker's public key that the attacker pushed to me saying, oh, I am Alice. So what would happen is that I would encrypt it with that attacker's public key, assuming that I am encrypting it with Alice's private key in the first place. But then that message will go to the attacker. So the attacker will be able to decrypt that message. So how is it ensured? And specifically, like if you are say trying to go to your Gmail, okay, so I am again not going to the details of it, but that means that there will be some way that public key will be used of the Gmail server. But how would you know that you are actually talking to Gmail server, not to any attacker servers? So there is a notion of what is called digital certificate, which ensures that you know that you are using the correct person's public. So that is how it is used, that one knows that if this is indeed Alice is claiming that it is her public key, there is a way to get it verified through digital certificates. So we are not going to it. We are trusting here that if Alice says it is a public key, I know somehow that it is a public. Is there any other question up to this?
Sir, so we are sending a pair of m comma m dash, right?
Yeah, you might ask why we are sending n.
No, no, sir. So that is to verify, right?
Yeah, right. But we could have said that I am not sending m at all. Okay, if I send something and if I decrypt, okay, then I will get back whatever I get was the message that was sent.
Yes.
But what was your question?
No, no, sir. So I was asking that m is the original
Okay, so you
message
see that one could have argued that why send m at all? Okay, that the reason why see that the argument could have been that I don't send m, I send only m prime, and Bob would decrypt it with Alice's public key, and whatever Bob gets would be the message that was sent by Alice, right?
Yes,
Okay.
sir.
Okay. So that could have been the argument, but the point is that you see that this whatever we are saying about encryption decryption, if I apply that that key, I'll always get back something, right? I'll get back some string as output. Now I do not know indeed whether that was what Alice had sent. Okay. Or I am just getting some garbage and that is what Alice had sent. Because you see that if an attacker, okay, traps this, and instead of sending that encrypted part, okay, that M prime, it changes it to M double prime and sends it to Bob. And then what would happen? Bob would try to decrypt M double prime with Alice's public key, and it will get back something, okay. And uh, instead of hello world, suppose he gets back hi world, so he would assume that Alice had sent hi world. Okay, so you see that one has to know that what was Alice sent. So the purpose of digital signature is not to see what actually was sent by so much as what actually was sent by Alice, but rather to verify that it was indeed sent by Alice. Okay, and also later on Alice cannot deny that she had sent it. Okay, also there is a little bit more to it which will come to, that it is what is encrypted will come to in one of the next slides. Okay, so
Yes,
the
sir.
part,
So,
sorry.
sir, the thing was that if we are directly sending the message with it, then anybody who is like uh, who wants to see can see, right? This message M.
Yeah. Very good point. I would have covered that a little later, but good that you raised the point. So now what happens is this whole MM prime, now Alice could have sent by encrypting it with the public key of Bob. Okay.
Acha. Okay.
So in that case, nobody else would be able to see it, but Bob will have to first decrypt that with his private key, then he gets MM prime, and then he does all those things. Okay.
Okay.
So that is how it will be. Okay. Very good question. Okay, so now what I'll do is that now I will again quickly show you that what happens for digital signature, right? So now here what happens is that I have generated these things. Okay, now let us see that Alice is sending to Bob. Okay, now we got this private key and sorry, I got uh, public key and private key. Now consider that it is Mr. X and myself. Okay, so what I said is that when I wanted to send something encrypted to Mr. X, as was rightly said, that I have to encrypt it with the public key of Mr. X. So this must have been the public key private key pair of Mr. X. Now the question is that I want to send that hello world, but now I want to send it through digital signature. Okay, not as an encrypted information. Now this public key private key pair is of whom? Is it of me or Mr. X? Sorry?
It is of me.
It is on me, right? Very good. So then what I have to do? I have to do like this. So I have to, what I'm doing is I'm simply copying that. And now this message hello world, okay. Then what I will do is that I will encrypt it here. So I select it and replace it and say here I have to click that it is a private key, and then I will encrypt, okay. So I'll encrypt it. So now what happens? This is the encrypted output. Okay, I am selecting that. Now what I will do, I will send to Mr. X that hello world. Okay, I'm sorry. That okay, send that encrypted text in sorry, that hello world in plain text. Okay, and then what I will do is that I will send that encrypted okay, that was encrypted with my private key, which I have pasted here. So this is what was encrypted with my private key, and then here I am pasting my public key, which is known to everybody, and then I am telling, and then Mr. X is trying to decrypt. So Mr. X got hello world in plain text, and he got this cipher text, which was encrypted by my private key, and he enters my sorry. So that is okay. So I'll show you that. So you see that what he should get. Anyone? What would be the output?
Hello world.
Okay, but what you have got? Yeah, so there was issue because you see I did not change this to be the public key. So this is supposed to be my public key. So if you encrypt it with the private key and try to decrypt with any other key, assuming it to be public key, it will not work. But now that I have mentioned it is public key, you see I get back hello world. So this is actually when I say I, it means that Mr. X is getting back hello world. So what he gets, he sees that hello world was sent in plain text, and whatever was sent in ciphertext when decrypted with my public key, it gives me hello world, the two match. So he knows that so this hello world was not tampered in between, and also because this decryption worked with my private key, sorry, my public key, so that means the message must have been encrypted with my private key, and hence it has been done by me. So he knows that it was sent by me. And also later on, I cannot say that I did not send, because you would say, you see, you sent it, and I could decrypt it with your public key, so it must have been encrypted by your private key, and hence it must have been you. Okay, so I think that clarifies this thing. But okay, that see this encryption using this public key cryptography, that is actually computationally expensive, which we have not yet mentioned. Okay. So it is not trivial to encrypt very large messages with public keys. Okay, this public key cryptography, both encryption and decryption. So what is done is that you do not actually send the message like this m and n prime. Okay, or rather, I'm sorry. So this m prime is not obtained by applying the encryption on the message itself. Okay, as on the left hand side we are showing that Alice is encrypting with this M, that is the original message, with her private key. It is not actually done. Instead, what is done is this, that Alice would generate a hash, the cryptographic hash as we have studied, of M, and then encrypts that with the with her private key. Okay, so now what happens? This S that was generated, that is being sent along with the full message M. Okay, the full message M is sent, but the signature is not a signature of the full message M, rather it's a signature of the digest of the original message. Okay, so you see that, so that is what I was saying, that here we said M and M prime, but there is a reason also, additional reason, is that the M is sent this to Bob. Okay, but the signature that is there, that is basically the, as we see, that it is encryption of the hash of it. So what can now Bob do? What Bob will do is that will apply the public key of Alice, okay, on S, okay, and will get something. Okay, he gets HM. He doesn't yet know whether M has been tampered with in between. So what Bob would do, will now apply hash on the M that he got, okay, in plain text, and that hash that he gets on that, that should match with this HM he got by decrypting the signature with Alice's public key. If these two match, that means what? That means you see that the two hashes match, and as we have studied before, if the hashes match, then it is safe to assume that the messages also match. So that means that nobody else could have sent it, because I could decrypt it with the public key of Alice. Okay, and the content of the message could not have been changed during transmission. That M has not been tampered with, because the hash of that message that I get matches with the hash of that message that was generated by Alice. Okay, so I means Bob here. So what Bob gets as the hash of that M matches with the original hash that was created by Alice on her side. Okay, because these two are matching, hence Bob knows that the message is that M. Okay, that is not encrypted. Okay, and indeed it has not been tampered with, because its hash that was sent by Alice matches with the hash now what Bob is generating. Now again, the whole thing, this M and S, as one of you asked, that now it can be also further encrypted with the public key of Bob, and he could first, as a first step, could have decrypted that to obtain the information using his private key, and then applied all these steps. Okay. So what we'll do is that We will again take an example, okay, to explain the concept. So let me go to the application once again. We'll do a little differently. Okay. So let me. So now because we have a hash, so now I will combine yesterday's demo with today's demo. Okay. So then things will be clear. Now let us see that again that I am trying to send hello world to Mr. X. Okay. So as we have said that and we are trying to do digital signature. We are not trying to do anything about further encryption using Mr. Hash's public key. Okay. So let us consider that. Now so in this example, once again, because I am trying to digitally sign, so this referred to my public key, private key, and then I want to send hello world, but assume that, as I said, that it is too expensive to encrypt this hello world. Assume it's a very long message, and I don't want to use public key for encryption of this hello world. So what I do is that this hello world, whatever text I have, okay, what I am doing, I am trying to generate its hash. Okay, hash, and I get that hash value. So that is the first step. So I get the message digest. Okay, so that is the message digest, and then this message digest is the text. Okay, that will be used to encrypt. Okay, so this is I paste it here and I get this plain text. Now you see my private key will be used to encrypt this message digest which I got as the hash. Okay, and this is now encrypted. Okay, now of course when it is encrypted I get something different. Okay, so this is what is obtained here. Control C, and so this is now going to be transmitted to Mr. X, and Mr. X is using my public key, and when Mr. X uses his public key, then tries to decrypt. Okay, so he will get back this message, and which of course, as you see, that this is what he got here. Okay, now of course, what else we will do? He also got this hello world. Okay, that I sent in plain text, and he also got this decrypted output. And what he will do? He will simply go again to this application, type in hello world, and generate the hash value. And what he gets here, he will see that this A591, etc., whatever it is, that matches with that A591, whatever he got by decrypting using my public. So he knows that the hello world that was sent, of course, was itself sent by Alice, and there it was not tampered in. Okay. So this final step, as you could see, that he got this through decryption using my public key, and then the other step is he would also apply the same hash function on what was sent this hello world as plain text M, and would get back the same hash value. So that is what we see how things would really work, and the whole thing gets back to this set of slides. So I believe that you have been able to follow. Is there any question? And also you see that once we get the digest, it's of a fixed length up to 56 bits, and it will be very easy to encrypt it and send. Okay. Of course, the encrypted length will not be small. That would be determined by the encryption key and other stuff. Okay. But rather it is the generation of the encrypted message. Okay. That is going to be otherwise expensive. So what is the use of digital signature? It is used to validate, in the context of blockchain, used to validate the origin of a transaction, prevent non-repudiation. So Alice cannot deny her own transactions, as we have mentioned, and one else can also claim Alice's transaction as his or her own transaction. And there are different ways of cryptography, like we talked about RSA. There are other methods and all for public key cryptography, like DSA. And so we are not going to go into that. So these are more for hardening the encryption and ensuring that it is not easy to tamper. So, for example, if let me give you some background now about what we said about the transactions in a block. These transactions, typically in the context of Bitcoin, these transactions in a that go in a block, will of course have more details of it later. Are the say that Alice generates some coins. Assume that Alice could generate coins on her own. Okay. And then say Alice generates 10 coins, and later on Alice makes a payment to somebody else. So we'll see that when Alice first generates, so Alice would generate these 10 coins, so that is the transaction, and with she can sign with her private key. So that is what is shown here in the box as sign with the private key. So this transaction is Alice generates 10 coins, that is the transaction. So that is like the message, which is signed by Alice with a digital signature. And then, and the digital signature, now you understand, is basically generating the digest, then encrypting it, and then this message along with the encrypted digest, that basically serves as the digital signature in short. So the transaction is signed by Alice's private key and put in the blockchain. Okay. So that is what actually goes in as transactions, as we had tried to show in that example of Merkle tree, and we'll discuss this. So that was in the previous set of slides, as we had seen. Okay. So it was there in this example. So what we are showing here as these transactions T1, etc. These are actually now same as signed this information, which will go in as transaction. Now suppose Alice transfers, okay, 5 coins to Bob, then this is what we have. So maybe it went to another block. So this example shows one transaction in each block. Actually, there will be more transactions. So Alice, what Alice does is that pays those 5 coins to Bob. So Alice pays B5. So that is the transaction, and it is again signed using the digital signature of A. Okay, and now you see that these are connected by those hash pointers. And if now somebody changes that A10 and its signature, so of course as the signature, if somebody wants to tamper, that will get detected from signature of Alice, and further it will be detected through breaking of the hash pointers and so on, which we have already discussed. And again, the next block will be pointing to this and so on. Okay. Also, what is important is that because Alice has signed this transfer of 5 bitcoins to Bob, and that is very important, that later on Alice would not be able to deny that she did the transfer. Okay, so that is how one can ensure non-repudiation in the context of blockchains, and that is how we have seen that how we can make use of these basic cryptographic primitives in the context of blockchain. There is also some use of the public keys of individuals, other than, of course, doing the decryption of the digital signatures. We'll see later that public keys can be used as addresses of the recipients. Here we are simply writing Bob, but Alice is paying to Bob, or it is Alice, and so on. So later on we'll see that instead of actually writing Bob, so what is the identity of Bob? So that could be the public key of Bob. So that is when we talk about bitcoins later. So uh, so basically the cryptocurrencies, how they are done is that, like the way we saw here, that this someone generates these coins and then makes payment. So in the context of Bitcoin, the first Bitcoins were actually generated by Satoshi Nakamoto, as we said, that whoever it is, and then it was made, the first payment was made, and then later on people actually do work and generate more coins. So that is what is mentioned here, that you generate new coins with time. So we'll study those things, how new coins are generated, and we, in order to maintain economy, the old coins are deleted, so that there is a fixed flow, not a not an indefinite flow of currency, because that would lead to inflation and all that. So some of the coins are deleted and so on. So this is unlike, just to conclude my slides here. So let me give you a bit of the background so that from here Professor Chakraborty can take up. Is that if you see that why this Bitcoin itself was started. So you see, whenever we have any such form of transactions, say online, okay, that is typically a trusted third party, like say bank, or say if you want to make credit card payments through PayPal, or you are using say Paytm and so on, right? So Paytm, you are making a payment to me. Say you are transferring me 5 rupees. Let's not make it too high and create trouble for you. So it is just 5 rupees you want to transfer. Now I am not there with you. So what you need to do is that you have to take help of this trusted third party, that Paytm, which will do the transfer. Okay. So we are trusting Paytm to do the transfer, and apparently they are doing it for free. But it is nothing is free in this world. So what they are doing is that they are getting a lot of data, and that data is there in some sense they are always selling. Okay. So they are making money out of it. So based on the service that they are providing. So be it Paytm, be it your Facebook, you are connected to your friend, but it is not for free. Your information is always available with Facebook, and they are going to do some kind of money out of it. Okay, or even they push some ads and all based on your behavior. So these are basically your data is being used to generate revenue for them. So we are trusting them, but they are always definitely going to make money out of it. Right? So the notion of Bitcoin was that instead of having these third parties whom we trust blindly and who have all our data which they can trade with later, so how we can have a completely decentralized system of handling money, in this case cryptocurrency, so that there is no intermediary involved, and all the users can will be at the same level. So any user will be potentially be able to get money and will be able to send money, and that is how all these things, all this concept of Bitcoin was actually formed. And as you will see that the basic cryptographic primitives that we discussed, those are used in a big way in order to ensure that at the same time, while we say that there is no trusted third party, because the advantage is that if you, for example, transfer money, say you know that if you want to pay your registration fee, and at least maybe one of you might have faced it during this semester as well, every semester that students face. But although the number is coming down quite a bit in recent years, is that when you pay your registration fee, the money gets deducted from your bank account, but your DRP you do not see added in your passbook, right? So and it is being handled through some payment gateway and your bank and then IT Kharagpur's bank. So you have all these different intermediaries, and the point is that if something goes wrong, so IT Kharagpur says, "Oh, I did not get your money, but the money got deducted from your account." So you have these intermediaries to fall back on. So you can tell them, "Hey, by my bank, this is what I did, and then it got deducted, but it did not go to IT Kharagpur. They are saying they didn't get the money." So the bank is a place that you can go to, and the bank in turn can talk to the gateways and those things and can settle these accounts. But then all these are basically they are going to charge you for. Okay, either monetarily directly or through kind, like your data is actually being sold. Okay. So the point is that if we do not have any such centralized authority, then how would you ensure that whatever transactions are getting carried out, they are carried out correctly, and also there should not be any issues, and these issues can also be solved through the system itself. Okay, and this cryptography plays a big role, especially as we have seen these hash functions and digital signatures will play a big role in ensuring that. So there will be these questions. We'll talk about how to distribute the coin management in completely decentralized peer-to-peer type of network. That I come to the end of this set of slides. If you have any question, I can answer. Otherwise, Professor Chakraborty will take it. Okay, if there is no question, so maybe Professor Chakraborty will talk now about some more details of blockchain. And if anyone has any question later on, you can always send mails or here in MS Teams, and we'll answer. Okay, so now, Professor Chakraborty, I am stopping sharing my screen. Yeah, I have stopped sharing.
Okay. So thanks, Professor Sural. So let me just share my screen. Okay. So, so till now, Professor Sural has explained to you the basic kind of cryptographic primitives that we typically use in the design of a blockchain. And then at the end, he touched upon the concept of Bitcoin and then how it actually worked as a kind of precursor to the design and development of blockchain. So let me start with a kind of a bit of history about how gradually this concept of blockchain evolved and how people have started using it for different kind of applications. So as Professor Sural was mentioning that the initial phase of blockchain was actually used cryptocurrencies at the beginning. But how it got coined as a kind of backbone technology for Bitcoin, and then what kind of advantages did it provide in the development of Bitcoin, that we'll see here in details. Okay. So, if we try to look into the three pillars behind the development of this blockchain technology, they are first the distributed systems, the second one is the cryptography, and the third one is some interesting economic models. So, one of the interesting fact behind this blockchain is that although we have started hearing it, although people have used the term blockchain after Satoshi Nakamoto published that white paper on Bitcoin in 2008. But these concepts are pretty old. So from 1980s, people started doing research on this kind of topic, and even there are classical techniques that are nowadays used over blockchain. So what I will try to do, I will try to give you a kind of journey about all those different classical topics that have been invented in the literature, and gradually you will see that how it contributed in the development of blockchain. So let us start what is our core problem in the design of a blockchain. So I have a network. So it is a kind of network of peer-to-peer system. That means every node is connected to its other peers over some communication link. Remember, it's a kind of a overlay network. There may not be a kind of direct physical where that is connecting between two nodes, but it is a kind of logical communication that is there between the two nodes. So for example, I am connecting to your machine currently over this Teams platform. So that way, there is a kind of overlay peer-to-peer network. And in a typical blockchain-based architecture, what we have seen earlier, that every node maintains a copy of the blockchain with it. Now, what is the problem here? So earlier we have seen, so whenever Professor Sural was describing about connecting different blocks with the help of that hash pointer, what we have seen that the structure looks like pretty similar to a linked list. The only difference is that rather than making it as kind of using a simple pointer to point to the next block, what we are actually doing, that we are using a hash pointer to point to the previous block. Well, in a way that the hash function is used to compute norms based on the hash of the previous one. Right? So that way, the structure is pretty simple, and the structure is a kind of similar to a linked list. Now, in case of a blockchain-based system, every node it maintains that particular structure, that is the blockchain. And now, my problem is that when one node, say here in the example node 2, propose a new block and add it to its own blockchain, this information needs to be propagated across the network, and everyone needs to agree on this new block. Well, so that means node 2, it is proposing a new block with its local blockchain, saying that, well, hey, I am going to connect this new block with my blockchain, and it propagates that information to the network. Well, based on certain networking protocol like gossiping. Gossiping means it is a kind of, I am broadcasting it to my peers, then my peers are broadcasting to its peer, and that way it gets propagated in the network. Well, so for example, here we send it to 1, 3, 4, 6, then 4 will send it to 9, and its other peers. But what I need to ensure that other nodes in the network need to agree on this new block. They should verify, they should be able to verify that this block is correct, and this block has been originated from a valid node called node. Well, if they are able to verify it, then they will add that new block to their own blockchain, and that way we'll be able to ensure that everyone has the same copy of the blockchain. So this is actually a kind of classical problem in the domain of distributed systems. So in distributed system, we call it as the consensus problem. So what is meant by consensus? Consensus basically means that everyone in the network should agree on a common information. So in a blockchain-based system, my common information is the newly proposed block. So everyone in the network need to agree on that newly proposed block. So what is meant by distributed consensus? Let me explain it with the help of an example. Say you are in a kind of party, well, where there are multiple different peoples, and there are two options. Either everyone can choose pizza or everyone can choose burger. Well, so either you can go to a pizza shop or you can go to a burger shop. But what they have to ensure altogether that everyone either go to a pizza shop or everyone goes to a burger shop. Well, now everyone has their own preference, their personal preference. So some people will prefer pizza, some other people will prefer burger. Now in this case, my objective would be to come to a consensus. And remember that in a typical distributed system, I do not have a kind of coordinator. If I had been a coordinator, so if I try to solve this problem in a centralized manner, so it might happen that, say, we are having a physical class. After the physical class, I can either go to the CCD or I can either go to the subway, and I as a coordinator, I as a central person can ask all of your choice, and everyone submit your own choice. Then I can basically try to find out what is the choice of the maximum people, whether it is CCD or whether it is subway, and then we can collectively decide that, well, let us go to subway if everyone agrees on subway. But here the problem is that I do not have any kind of central coordinator. Everyone is a kind of leader here. Everyone wants to try to take the decision simultaneously. Right? Now just try to map it in a kind of practical scenario that how you are actually going to solve this problem. So what we are typically going to do that everyone will share the information with each other. Well, and try to find out that, well, what is the maximum choice of the maximum people. Say if the choice of the maximum people is burger, then we say that, well, the system has reached to a consensus with an output of burger. So let us go to the burger shop. But the question comes that how I can solve this problem in a distributed way. Well, the way to solve this problem in a distributed way is that what we can possibly do that everyone informs their choice to other. Well, say this lady, it sends its choice to everyone others that I prefer burger. Well, then the other person, he informs his choice to others that, hey, I prefer pizza. So that way, everyone collects the choice of others and try to apply some local function. Say the local function here is the kind of a maximal function. So everyone tries to individually find out that, well, whether everyone is or others are saying pizza or burger, whichever is the maximum, we'll decide upon that. Right? So the protocol can work in this way. Now, this particular protocol can work fine if everyone is a perfect person, everyone is a non-malicious, and they can decide it in a correct way. Well, so no one is telling any kind of lie. Well, but in a real system, what might happen that some person can behave maliciously. For example, one can say that, hey, you told pizza, and that person can say that, no, I told burger. Well, so that kind of scenario can appear in a real environment or a real system. And the question comes that how can we still reach to a consensus under such kind of environment? Well, so this kind of typical environments are called a kind of faults. Well, so there are different type of faults that are being modeled in a distributed system. So later on, whenever we are going to details about the different kind of consensus algorithm, we are going to see that what the different type of faults can be in a typical distributed system and how a distributed consensus algorithm can solve this particular problem, that when someone is trying to tell a lie or someone is just denying the information that they have shared. Right? Now, the interesting fact is that this research on the distributed consensus started around in the year of 1980s. Well, so in 1985, there was a kind of very pioneering research paper from Fisher, Lynch, and Patterson. They published an idea, or rather they published a theorem that is called the FLP impossibility. So the FLP name came from the inventor of this theorem, Fisher, Lynch, and Patterson. And what this FLP impossibility theorem says, that consensus is impossible in a fully asynchronous system, even with a single crash point. Well, now what does it mean? So here we have a term called asynchronous system. So what is meant by an asynchronous system? The asynchronous system basically means that whenever you are transferring some kind of message, so what we have seen earlier, that the way to reach in a distributed consensus is through message passing. That means I am sending a message to all my peers or all other peers in the network saying that what is my preference. So that way, everyone is sending this message to other peers in the network, and that way they are going to decide it collectively. Well, so message passing is the key in the distributed consensus. Now, depending on this message passing, we can model a distributed system in two different ways. One is called as the synchronous system, another one is called the asynchronous system. Now, what is a synchronous system? A synchronous system basically says that I have a finite bound on the delay and all the messages will be received by that time. Well, so that is a kind of assumption of a synchronous system. Well, that every message will be received within a finite time, and that time window will be kind of small time window. It should not be kind of infinitely large window. But what is an asynchronous system? Asynchronous system doesn't make any such kind of assumption. So it can consider that a message can arrive any point of time, or the message can see arbitrarily delay while getting communicated. Now, what you can see that our real networking systems are kind of asynchronous systems, that we cannot give a bound on the delay of the message. So the message can see arbitrary delay. Some message can be received very fast, whereas some other message can be received very late. Now, how it is impacting the decision in a distributed consensus? Now you see that whenever you are talking about this algorithm, that everyone is going to say their local choice to other, and based on that, I am going to take a decision whether to choose for a pizza or whether to choose for a burger. Here, in this particular environment, I will be able to take the decision only when I will receive the information from all my peers in the network. Well, then only I'll be able to take a decision, then only I'll be able to put a maxima function to find out whether maximum people are choosing pizza or the maximum people are choosing burger. Now in a synchronous system that is fine, right? Because you will have a kind of finite delay, and within that finite delay you are guaranteed to receive all the messages. So you are guaranteed to receive the choices from all other people of the network, so you can make your decision. But in an asynchronous system, you cannot give that guarantee. You do not know when the messages are going to come. So what you have to do, you have to keep on waiting until you are getting the last message. Well, now here comes the point. So what FLP impossibility theorem says that even with a single crash fault in an asynchronous system, consensus is impossible. So you can just, so they have given a formal proof. I am trying to explain it logically. So logically now you can think of that in an asynchronous system, because you do not have any kind of bound on the kind of time by when you are going to receive the message, what can happen that every message can see arbitrary delay. Now if a node fails, okay, so if there is a kind of crash fault means suddenly there is certain problems in one of the participants' network and that participant is not been able to send any message. Well, say assume that there is a kind of network cut or there is a kind of power cut. Well, and the participant is not been able to send the message. Now, if the participant is not been able to send the message, then the other persons are waiting for infinite amount of time. They will not be able to decide that what is going to be the final decision, whether to go for pizza or whether to go for burger. Okay? Because they have to wait until they are going to receive all the messages. So that was the kind of thing which was formally being proven by this FLP impossibility theorem, and it worked as a kind of pioneering baseline behind the design of this distributed consensus algorithm. And it basically says that this consensus is impossible in a fully asynchronous system, even with a single crash fault. Well, now whenever we are saying consensus is impossible, that basically means we will not be able to ensure the two important properties of a distributed consensus. What are those two properties? The two properties are safety and liveness. Well, so what does safety means? Safety basically means that the correct processes will yield the correct output within a finite amount of time. Well, so that basically means that in a network, well, there might be nodes which are faulty, there might be nodes which are malicious, but the nodes which are behaving correctly, they should be able to produce the correct output within a finite time duration. So that is the property being guaranteed by safety. And what is meant by liveness? That this amount of time, that the output will be produced within a finite amount of time. So I am not putting any guarantee that whether the output is going to be correct or not. So even they reach to an incorrect output, that output will be produced within a finite amount of time. That basically ensures the eventual termination of the algorithm. Well, so that means the safety property guarantees that the processes will reach to the correct output, and the liveness property guarantees that, well, this output will be processed within a finite amount of time. So the algorithm will eventually terminate. So if I just combine these two properties together, safety and liveness, it says that the algorithms will eventually terminate by producing the correct output. So in a fully asynchronous system with a single crash fault, we will not be able to support safety and liveness together. So how does FLP impossibility theorem actually help in the design of distributed consensus? Well, so the people understood that, well, in an asynchronous environment, and as I was mentioning that a real networking environment are typically an asynchronous environment. So in an asynchronous environment, we will not be able to guarantee safety and liveness together. So what we can do, let us prioritize one over another. So either give a priority on the correct output, or let us give priority on termination of the algorithm. Well, so the existing distributed consensus algorithms, or in 1989 basically, Leslie Lamport, I guess that at least all of you have heard about his name, at least the people who are from the computer science background, they should heard about his name. He is one of the pioneer in computer science, in algorithmic design in computer science. So Leslie Lamport, he started talking about an idea called Paxos. Well, the idea of Paxos was that Paxos, that distributed consensus algorithm, it will support safety but not liveness in the presence of such crosstalk. Well, so he has given priority over safety, over liveness, and tried to design a distributed consensus algorithm which might not terminate, it might have infinite number of loops, but the outputs that it is going to produce, or maybe the intermediate output that it is going to produce, those output will be the correct output. But the interesting fact about this particular algorithm was actually in distributed system literature, Paxos is not a single algorithm, that rather it is a kind of set of algorithms. Later on, we'll discuss Paxos in details. During that time, we'll discuss those algorithms in details. What was the core idea that this set of algorithms will always provide much weight on safety compared to liveness. And the interesting fact was that during this entire period of 1990s, around for 11 years, people are very much confused about the correctness of Paxos. Well, although there are multiple paper submission, research paper submission in different conferences and journals from Leslie Lamport, but all those papers got rejected for almost 10 years, mentioning that people couldn't validate the correctness of that particular algorithm. Well, so the reviewers were utterly confused about the correctness. Well, so that was a kind of interesting fact, and that actually means this. I would rather say that this intention of Lamport, that he didn't leave that problem, and that he tried to find out a kind of more understandable justification, more understandable proof behind the correctness of Paxos. And finally, in 1998, this Paxos paper got published in SCM Transactions and Computer Systems. So that is actually one of the milestones behind the history of distributed systems. So one research article that got floated for nearly 1 decade, that means nearly for 10 years, and people were confused about its correctness proof, and finally people agreed and that paper got published. Well, so this actually put up this milestone, and then in 2001, this FLP impossibility paper that reached the Dijkstra Prize, and Dijkstra Prize is one of the best prizes in the area of computer systems, or even in the area of computer science. And from that point of time, people started talking about distributed systems. People thought of that well, and people started realizing the importance of distributed systems. Well, and the research of distributed system got and started to see more amount of research from different researchers across the globe. And gradually, in 2009, there was this software called Apache Zookeeper that got released. That Apache Zookeeper was a service for managing the different kinds of distributed applications. There was tremendous applications or tremendous use cases where Zookeeper had been used in practice. And then from 2010 onwards, different type of consensus algorithms that was released. So people started designing different notions of distributed consensus, and various algorithms like multi-Paxos, RAF, Byzantine fault-tolerant algorithms, PPFT, practical Byzantine fault-tolerant, all these algorithms came into the market. Well, so that way, this distributed consensus of the researchers in distributed system have seen a kind of long path for nearly 30 years about finding out that how I can reach to a consensus where different people have different choice. Well, a different node in a network has different choice. So from the perspective of blockchain, what you can see here, that this distributed consensus algorithm can possibly be the answer to my original question, that in a typical environment where one node proposes a new block, how would I ensure that every other nodes in the network can accept that block by reaching to a consensus? Well, so today I would like to stop here. In the next week class, next Wednesday class, I will pick it up from here and we'll see that what kind of revolution these ideas of cryptocurrencies and primarily the Bitcoin put into the core idea of this distributed consensus that made blockchain much more popular in the community. Well, so here actually for the time being you can see that the problem of this consensus in a blockchain network can be solved with one of those distributed consensus algorithms because they are telling about pretty much the similar. Well, but this Bitcoin actually put up a complete different notion of consensus that helped us in making this particular technology or the blockchain technology very much popular and bring up much more hype and much more myths about this particular technology. So in the next Wednesday class, we are going to talk about how this cryptocurrency got evolved. So that was a parallel track that got evolved. And finally, with the help of Bitcoin, this researches in distributed system and the researches in cryptocurrency that got merged and give the part of this concept called blockchain. Well, so any query or any question up to this point? Okay. If not, then let us let us close the class today.
One quick so
yeah.
next Wednesday actually is Institute Foundation Day. I think classes are
Right.
suspended. And 19th also is Muharram is a holiday. So maybe we are meeting next Friday, right?
Right.
So we'll send an email.
Yeah, based on the holidays and everything announced, we will send an email to us.
Okay.
Sir, I had a question regarding the definition of synchronous and asynchronous environments.
Right.
Sir, if in a system, instead of a deterministic time, the nodes are kind of waiting for a random amount of time for the messages to arrive, then will that be considered an asynchronous environment or a synchronous environment?
Asynchronous environment, because this that actually depends whether you are being able to put up a threshold on the message passing time. So theoretically, that threshold can be anything. Means if you are being able to put up a threshold which is sufficiently large, say for example, even if you are being able to put up a threshold for 10 days, you can call it as a synchronous system by definition. That within 10 days you are guaranteed that you are going to receive all the messages. But in a networking system, from all practical purpose, you cannot put that large threshold. Well, we need to be a kind of realistic in that environment. So theoretically it is true, but in practice, if you are having a random amount of time, but if that random delay is unpredictable, well, if you cannot find out a bound on that random delay, then we call it as a kind of asynchronous.
And sir, the nodes are